Hey students, today I'm going to be discussing how to use the Pythagorean theorem to help solve a right triangle. So I'll discuss what all that means really quickly. First, by starting off with the Pythagorean theorem. So as most of you may already know, the Pythagorean theorem goes like this: a squared plus b squared is equal to c squared. And it's particularly applicable to specifically triangles and specifically right triangles. So let me just pull this up really quickly. A right triangle is just a triangle that has a right angle. So notice this 90-degree angle in this particularly drawn triangle would be called a right angle. So this would be called a right triangle. And any right triangle satisfies this particular property, which is called the Pythagorean theorem. And a theorem is just a mathematical word for something that is true, a formula that describes, in this case, the shape of a right triangle. So if we look at what the theorem says, a squared plus b squared is equal to c squared, this is the equation, sort of the result of the theorem. And actually, part of a theorem is proving the validity of this formula, which we're not going to do, but basically you have to take the word, take our word for it that this formula is true. And some of you might be wondering why is it called this? It's named after mathematician, philosopher Pythagoras. This dude from long ago, Greek, probably heard of Pythagoras before, but there's actually no proof that he actually was part of this formula, and there's proof that Babylonians and other ancient civilizations knew of this principle, a squared plus b squared equal to c squared, to some degree, and had used it to solve problems. So nobody's really sure exactly why it's called the Pythagorean theorem, but it is attributed to him, and it's thought that him and his students constructed the first proof of it. Again, no evidence of that, but anyways, it's called that, and this is again the result. So here, let me explain how it works. So the theorem goes: a squared plus b squared is equal to c squared, meaning that if you take if you take one leg of the triangle, essentially this side a, whatever that length of this side would be, say 5 or 10, whatever it is, if you square that, you add it to this side over here, b squared. So let's say that this was 5 and this was 6. You would take this 5, square it, so 5 times 5, and you'd add it to this one squared, 6 times 6, whatever it is, and that would give you a squared plus c squared. And saying that the sum of these two sides squared has to be equal to whatever this third side, called the hypotenuse, is squared. So in this case, any right triangle has to satisfy this principle. And the way we can solve a right triangle is if we know two of the sides, we can kind of stick them into the formula and figure out what the other side must be. Again, because this Pythagorean theorem is an equation that has to be true. So let's look at a couple examples of solving right triangles using the Pythagorean theorem. So one example would be, let me draw a slightly different triangle like this. Say it has a right angle right there. You can excuse my drawing skills, but let's say we had two sides 6 and 8. Say that side, 6 inches or feet or whatever. I'll just say 6 units for the left-hand side of that triangle, 8 units for the top of that triangle, and we want to know what is the third side. And again, we can use the Pythagorean theorem to help us solve the third side of this triangle, because the sum of the squares of each of those two other sides, 6 and 8, should be equal to the third side squared. So essentially, what we can do is we can plug the numbers that we do know into the formula and solve the last unknown side by solving the equation. So in this case, one thing to be aware of with the Pythagorean theorem, pulling back up my picture of the Pythagorean theorem, is that C is called the hypotenuse, and C has to be the longest side of the triangle, and it's always across from the right angle, meaning away from it. The two legs are the two sides that are attached to the right angle. Those always have to be A and B, and actually A and B, it doesn't matter which you call A and B, but usually B is the middle and A is the small, but it doesn't particularly matter. But anyways, the two legs are attached to the right angle. The hypotenuse is the long side across from the right angle. In this triangle, it's drawn a little differently than that other one. But in this case, the 6 and the 8 would be the two legs, because they're the two that are attached to my right angle there. And also, and that makes the third side over here the hypotenuse of that triangle. Also, since it's across from the right angle, that guy has got to be the hypotenuse. And again, the hypotenuse is always c, so it will always be the right-hand side. The c squared portion will be this. So essentially, I'll call this unknown c. That's my hypotenuse in this example. So we would have a squared plus b squared equal to c squared. Again, what I said is that a and b, you could choose either leg. So let's just call a this side 6 and b this side 8. And basically we stick those into the theorem. So we have the a squared, a is 6, so 6 squared plus b squared, so b is 8, is equal to c squared, and c is the one that we do not know. So we have 6 squared plus 8 squared is equal to c squared. So then we can just evaluate these values. So 6 times 6 is 36, 8 times 8 is 64, and that would give us 36 plus 64 is equal to c squared. Adding those two numbers together, we get that 100 is the sum of 36 and 64, so 100 is equal to c squared. And finally, what we'd be tasked with solving would be, well, what squared? C squared has to be equal to 100, so what squared makes 100? And many of you probably know that 10 times 10 is 100, so 10 squared makes 100. Essentially, this gives us the answer that c has got to be 10. And so if you're wondering how can I solve my equation for c, how do I get rid of the square, what's nice is we can use the square root function to cancel out the square function, because remember, the square root does the opposite of the square. Squaring a number makes it larger by a factor of whatever the original number was. Square rooting does the opposite. It takes it back to the original. If the number was a perfect square, it would take it back to whatever squared made the original number. Anyways, if we took the square root of both sides right here, essentially what we would get would be square root of 100 is equal to the square root of c squared, which technically is absolute value c, but for the sake of this class, we just take this one. We'll just say that the square root of c squared cancels, and so we get c is equal to square root of 100, or 10, as our third side. So we get that the third side over here has got to be 10, and that's how we do it basically. And you can check to make sure it works, but basically when you square this side and you square that side and you add those together, so 6 squared is 36 plus 8 squared is 64, that's got to make this third side squared, which is 100. So it adds up. Again, that's what essentially the Pythagorean theorem in a nutshell. So doing one more example. So on your practice test, there's an example, and we looked at it a little bit in class, but let's rewrite it here. So I believe we had a right triangle something like this, where you're given this side is 5, this side is 13, and this side is our unknown side, x. And I say find x, solve for x, using the Pythagorean theorem. So this one, it's very similar with a little bit of a difference. But again, first we would want to identify the hypotenuse. Hypotenuse is always opposite of the right angle, so the hypotenuse is the longest side. Well, if we look at the lengths here, it looks like the top of this triangle is larger than the bottom side, so that sort of horizontal, that 13 is larger than the x, just eyeballing it. Again, however, the two ones attached to the right angle have to be the two legs. So a and b are those two sides. So if we look at a squared, again, starting with the Pythagorean theorem, because this is sort of the principle that defines a right triangle, we plug in those two sides. The two legs are a and b, so we'd have 5 squared plus x squared is equal to c. The hypotenuse is the other side across from the right angle, not attached to it. So 13 would be c, and so we would get our, we just plug in those three sides, and the unknown side is x, and that's what we're trying to figure out. So evaluating each of the squares, 5 squared is 5 times 5, x squared we do not know yet, and 13 squared is 13 times 13 is 169. And so from here, this one's not exactly the same as the last example, because in this equation we have 25 plus x squared is equal to 169. So we actually want to, if we want to solve this, we can't take the square root yet, and there's sort of a more algebraic reason why, which you'll get to in algebra. But essentially, if we want to solve this, we could isolate the variable term. That's one thing we like to do with an equation, is get it alone. If we can get it alone, we can solve it. So the way we can get it alone is if we get rid of this number, subtract 25 from both sides. That would give us that x squared alone on the left side. So we'd have x squared is equal to 169 minus 25, which is 144. And then the last thing we'd be tasked with trying to figure out is, well, what squared, x squared, has to make 144. So that second side on the bottom squared should be this 144 number. And again, we could take the square root of both sides to figure this out. So if we took the square root of both sides, remember that the square root and the square cancel each other out. So essentially that's how we get x by itself, is by taking this square root. And the square root of 144 is 12. 12 times 12 makes 144, and that gives us the last side of our triangle, in this case x being 12. And so sort of to check yourself, what you could do is you can always square the two legs of your triangle. So 5, and then we've solved x to be 12. We square that as well. 5 squared is 25, 12 squared is 144. When we add those together, 25 plus 144, we get 169, which has to be this third side squared. That's what the Pythagorean theorem says. So, if you can remember the formula, a squared plus b squared is equal to c squared, just remember that c has to be the hypotenuse, and then you can just use that sort of mathematical formula to it. And one last little tidbit on this is most random numbers, if we just throw random numbers into our triangle and try to figure out sides based on it, most numbers will not work kind of as nicely as these examples do. In these examples, we always get whole numbers, but this isn't always the case. So just to throw one last little example at you, and you need a calculator to do these questions because, well, I mean, not need, but it's very difficult to find square roots of numbers that are not perfect squares. But just sort of as the final example, say I have a triangle like this, and this side is 9, and this side is actually, I don't want it to make 6. That's going to be actually right. But let's say the second side over here is 7, say. So sorry, my pen is not working. There we go, 7. And this guy here is our right angle. So again, our third side would be C. Across from the right angle has to be our hypotenuse. Using the Pythagorean theorem, again, starting with a squared plus b squared equals c squared. So in this case, C is our hypotenuse. So those other two are A and B. Again, it doesn't matter which is which. Let's call 7A and then 9B. So 7 squared plus 9 squared must make C squared. So in this case, 7 squared is 7 times 7, 49. 9 squared is 9 times 9, which is 81. And so in this case, our third side squared has to be the sum of 49 and 81, which makes 130. And 130 is not a perfect square. No two numbers no number multiplied by itself makes 130 naturally. So, because 11 times 11 is 121, 12 times 12 is 144. So 130 is kind of by itself. There's no sort of natural square root. So as we try to solve for C is equal to the square root of 130, which is called an irrational number because it has no natural square root. There are things that can be done to certain square roots like this when you get into further in algebra. It's called simplifying a square root. But for now, if we wanted to figure out what this was precisely, we would need to type this into a calculator. So just to pull up a calculator really quickly. Where's my calculator? Well, anyways, square root of 130 is somewhere between the 11 and 12. It's probably going to be about 11.3 or 4, something like that. You need a calculator, but sometimes we would just leave our answer like this: the square root of 130, which is an exact answer, even though we don't. It might be hard right now to interpret what that means. It'd be okay. Again, this if you're in pre-algebra, you're probably not expected to do this unless you have a calculator. Which in my class, my pre-algebra class, we don't use calculators yet. So this question, on the test, will only ask you a question that you could solve without one, so wouldn't have to worry about this particular example. So let me know if you have any questions about the Pythagorean theorem or any of these examples in the comment board. Thanks for watching. Bye.